So this is going to be what we call example 2.1.7. This is called a mass spring chain. Okay, and what I want to show is, let's construct math models to capture data from, can you guess what I'm about to say? A real world problem. Well, what's a real world problem again? Something to measure with data. Could you guess what we're going to measure with data? A mass spring chain. What the hell is a chain? What is a chain? Something with links. So could you guess what a mass spring chain is? Linked masses and springs in a chain together. So here we go. Oh, don't worry. I have a bunch of springs in my portable spring bag that I carry around campus with me. I never wanted to be the spring, the bag man. You ever seen those teachers that just walk around campus with bags and boxes? I always promised myself I wouldn't be that person. And now I'm that person. And not only am I that person, like my colleagues have a bet if I have more bags than anybody else on campus. I'm like, well, I do have 2 scales that I carry around with me just in case one of them breaks, right? Okay, so here we go. Here's the problem we're going to study. Yeah, there it is. Oh. Do you feel the suspense building? You feel the tension? Oh, I should have used that one. That was my joke. You took that joke away from me. That was a good one. And maybe I'll use something a little bit lighter. Yeah, maybe I should use something a little lighter so I can have less resistance. Here. All right, so here we go. What are you noticing about the amount of time that real world problems take? Yeah, isn't it so much easier for me to just write stuff on the board? That's why mathematicians do that. This is expensive. It takes time, yeah. I mean, shall I be, what do you think, brutally honest or positive? Brutally honest. Okay, let's do both. Brutally honest, lazy. Positive, efficient. Right? Okay, so here we go. Here's the problem. Do you see that right now, so you kind of see this is a mass spring chain. Can I show you an eigenvalue problem? Sure. Here's an eigenvalue problem. Here we go. Ready, set, go. There's an eigenvalue problem. It's a very, very special, it's a forced eigenvalue problem. Anybody taken ODEs yet? Anybody taken Math 2A? Okay, in Math 2A you study the M U double dot plus B U dot plus K. Okay, this is 2 of those simultaneously in sync. So that means that this thing affects that thing and that thing affects that thing. This thing has a natural frequencies. In fact, here's one of them. Here's the other one. Those are all called eigenvalues. Don't worry. I just stole something from you. But you're actually witnessing live in class a real eigenvalue problem. Is this algebraic or differential? Why is it differential? You know what algebraic is, right? Does algebraic involve time? No, algebraic is like studying snapshots, right? Algebra means you study 2 distinct phases in time, and then you measure the differences and changes just based on those phases. You take one snapshot, look at the other snapshot, measure the distance. There's a scalar value that represents that. What's differential mean? Use a video camera. Now you study infinite number of frames, and you want to know what's happening to the individual things in those frames at any moment in time. This must be a differential equation. Why?
Because there's time.
Because it's not a photo. You want to see a photo? Here's an algebraic problem. Okay. Would you agree that gravity is affecting this thing right now?
Yes.
Why is it affecting it? Because it's on Earth. Yeah, that's true. Because Earth is very massive. But what I mean is, what's it doing?
It's pulling everything down.
It's pulling everything down. Okay. Should we eliminate gravity?
Yes.
Would you now say that I've effectively eliminated gravity? Now, I haven't eliminated gravity in the sense that it's not like I flipped off the gravity switch. But what did I do?
It's all pushing the same.
Gravity is now orthogonal to the motion of the masses along their axis in the springs, right? Okay, so what that means is I could actually right now, here we go, I'm going to take the center of mass. These masses are kind of funny. And I'm going to put a little 37 center of mass calculation that we spoke with. You'll talk about this later in class. I spent literally like 3 working days calculating center of mass, which is one parameter for an eigenvalue problem. Given. Come on.
Is that including like the hook on the end and everything? Or?
Oh, all of a sudden this isn't so easy, is it? Welcome. Welcome. Okay, that's called applied math, right? Okay, ready? Let's flip gravity back on. Okay. Watch what happened. So I'm going to mark the same thing. I should mark it in red, huh? I want. You know what I really want to do? Mark it in blue, but Amazon wasn't selling blue cartridges the day I bought them. Darn it. What do you notice?
Lower.
There's a shift. Okay. Do you see vectors? I see vectors. I see a lot of vectors.
1, 2.
Okay. I see at least 3 vectors. Okay. All right. So let's capture this real world problem. Maybe I want to bring it over with me. So should I walk across campus with this? Be like Vanna White? Be like, oh, you're trying to get to class for today and today only. This can be yours for just 12 weeks of your life. Okay, so here we go. Let's let M, could you guess what M is? Mass. Maybe we call it M1 and M2. All right. And then we're going to say that there's actually 2 M's. One of them is going to call the M observed. So this is going to be M1 and M2. And perhaps if I was too legit to quit, I would actually give you the exact values of these things. And in this case, in the example that I do in my notes, I actually did something that looks like this, right? So I did a, what is that? Probably a 20 gram, 200 gram, and a 100 gram. These ones I haven't measured yet today. I think these are supposed to be like 20 grams, so that would be 0.02, right? Okay. And then later on in the class, we're going to have something called MCalc. All right. Let me ask you this. Do you remember the 4-point diagram? What was the 4-point diagram? What was the one on the top left-hand corner? Real world problem. Whoa. Whoa. I almost looked really nerdy, but now I look like a dad save. Is that what that's called? That's what I call it every time I stop my toddler from falling off the couch. Call it a dad save, right? All right. Now we can call this a nerd. Okay. What's the real world problem? Do you see it? I want to know. So here's a real world problem. It's observable with data. What's the solution?
Measure it.
How long did it travel? Given the masses, how far did it travel? That's a linear systems problem. In fact, it's a non-singular linear systems problem. Right? Oh my God, that's a really good question. We should find out. That's a deep question, actually. It goes quite deep. Why is this non-singular? Why is it not rank deficient? Okay. Okay, could you solve this problem using actual, is there an observable solution to this problem? It's right there. But what if I told you I'm not going to actually predetermine the masses, I'm going to determine the masses off the top of my head? Once you leave this room, could you solve this problem? The only reason you could solve it now is because some nerd spent a bunch of time by himself solving the problem for you and constructing something that you could do it, right? Okay, what do applied mathematicians say when the cost of doing this is quite high? Instead of trying to jump from the real world problem to a real world solution, why don't we do what? Work around it. So first of all, what are we going to do? Model it. So let's go ahead and do that. Let's create an ideal model for this thing. And in that ideal model, we'll introduce some variables. Okay, so here's an ideal model. And what's the verb? Mathematize. And you might call it mathematization, right? Okay, so in this ideal model, what do we need? Well, let's take a look. Does this move or does it not move? Okay, this doesn't move. Well, I mean, just look at it. Come up right now. You want to see that it doesn't move? I tripped over this I like made my foot bleed, and the lady that was living under us at the time took a broom and hit the ceiling to tell me to shut up. I swear to God, that lady almost got a long talking to about linear algebra. All right, so we need something that's fixed. So this is going to be called a fixed ceiling. And then what about this? Fixed ground. Ooh, I like that. Okay. What else do we need? We need springs. Okay. Perhaps we call this thing M1. We call this thing M2. Okay. And then what did we say? We're not sure about this, but what did we say about each of these springs? It can be modeled by Hooke's law. Well, what is Hooke's law? So we're going to come back to this later in the course. Ooh, yeah, this one's non-trivial actually. The force in a spring is K times the displacement of the spring. So this is what we're going to call displacement. You got to be careful because this is not Fu, it's F of u, right? And then this is the thing that actually, you got to be careful when you say Fu because some people will say Hooke's law, but some people won't say that, right? So this is, do you remember what we call this thing? Spring constant. Yeah, spring constant. Stiffer springs have larger spring constants. So the K there, and I'm actually going to physically show you this because some of you might not spend your weekends playing with springs, and that's normal. Be proud of yourselves. Okay, do you see this? Let's do a really non-stiff spring to make it like, oh, that one's, yeah. Okay, here we go. So this is a super non-stiff spring. You see it?
Yeah.
So the K on that is going to be smaller than the K on the thing I'm about to show you. See how stretched that is? Okay. That's a stiff spring. So the K on this thing is higher than the K on that thing. How would I figure out what the K's are? Least squares problem. I would set up an experimental least squared problem by doing nothing other than staying in my room, shutting off my phone, and measuring springs and masses. Okay. Could you guess, if we have 3 of these, how many spring constants we need?
3.
Okay, we need K1, K2, and K3. What else did we need?
Displacement.
Well, yeah, strictly speaking, did we do displacement first?
No. That's a.
Yeah, so we had what we might call the t equals 0 time. How do I determine that it's t equals 0? Because I'm the determinant. You could also say t equals t0, right? It doesn't really matter when you do it, but maybe a good engineer would say, let's keep it simple. What did I do first? Turn off gravity. You know what that's called? Stable equilibrium. Point, no forcing function, no acceleration. So it's 0 net force, there's no forcing function, there's no extra information. Could you guess what we call that thing right there? Yeah, let's call x1 the position of center of, what am I about to write? At equilibrium. No motion, right? Okay, could you guess what I'm about to say now? Yeah, so this is the position of center of mass 2 at equilibrium. The moment I write position, what does that imply immediately? I have a ruler. Do I have a ruler on that thing? Yeah, so that I can actually measure positions, right? I forget at the moment, yeah. Okay, this is for Colin. Got really mad at me the first time I taught this class because I guess I violated a rule of physics. As a mathematician, I was like, yeah, but Colin, it's just a scalar multiple of what you're saying. And he's like, no, you shall never do what you just did. And I was like, okay, Colin, you've taken physics classes, I trust you. Okay, so could you guess what we do in our ideal model? First thing we do is we hold time constant, we turn gravity off, and then we just let the thing settle down. What could we do in our ideal model? Turn gravity on, or better, look at it at any time t. I'd like to do a general for now. Could you see that I can map this at any time t? And that the solution of the thing is actually called a function? Yep. It's called an eigenvalue problem. Don't worry, that's differential equations. Okay, so let's track position of center of mass. What am I about to write? At time t. And maybe you say t runs from the 0 position all the way to some ending position. Could you guess what we might call an end in an engineering system? Yeah, so capital T, you might say, is when the thing settles down to equilibrium under the particular constraints of your function. Anybody drive to school? You drive over a speed bump? You have a coupled mass spring chain. You actually have 4 springs, 1 mass called the car. When you went over the bump, what happened? And then they had something called the dampening force, which is usually a non-Newtonian fluid. And what eventually happened? It went, especially if you have a caddy, right? My grandpa has a caddy. It goes, dunk, dunk, real smooth, right? Okay, so let's look at this. Okay, what happens as the thing gets perturbed? I should really draw it right next to that thing so that you could see it, right? Maybe I'll do that here. What happens as I turn on gravity and let the thing settle? There's an offset. Okay, would you mind if I erase this for a second? I actually have a video on this waiting to be done. I just haven't set the schedule yet for you all to watch videos before you came here. But it's all, like I spent literally 12 hours for 5 minutes of film. Welcome to video production. All right, so here we go. So now this is M1. This thing stretches out a little bit. That's M2. What's going to happen at the bottom in this case? The spring compresses. Okay, and then maybe you have the same setup over here. So it's literally the exact same ruler, right? So literally the exact same points in the exact same position we'll call positive direction. So here you might call this ground of your measurement system, where this is the ground of Earth below you, right? Yeah, ground on Earth. And this is ground of measurement system. Okay, so now what? Yeah, so if we call this x1, could you guess what we call this thing? x1 of t. It's the center of mass 1 at time t. Let me ask you this. Can your eyes see that? Can you see that with your eyes?
Yes, but I can't measure it. You can't.
Sure you can. You can measure it, but I would claim that you can't see it. Mike and I could, if you gave us $100 right now, we could come probably in about 3 hours. I think we can come back with a 30 hertz measurement of exactly where that thing is in time.
Record it and then slow it down.
Oh, okay. But can you see it? So what was the main condition for applied math to make money? You have a real world problem that you want to understand, and then there's this solution that you want, but there was something in between. What was that? Cost, or AKA obstacle. Do you see the obstacle? It's too fast. Right? Or another one is switch out the masses, then what happens? Okay, so then what are we going to do? Mathematize. So here this is x2 of t. So what was x sub I of t? And we'll take a break right after this. This is the center of mass I at time t, where t ranged from the beginning all the way to the end. And what was the end? I think Morris in his 2A class would call it settling time, right? The time it takes to settle all the way down to no motion, stable equilibrium. Okay, last vector that we're going to introduce, and then we're going to take a break. Could you guess the, oh my God, that went fast. I thought it was going to be like 240 right now. Could you guess the last vector we're going to introduce? You said it earlier. Displacement. Okay, how do we say displacement? So first of all, do you notice that we can have a vector x1, x2? What is this vector? It's a 2 by 1 vector that captures the positions at equilibrium with no gravity. Okay? Okay, so that's what we're going to call the equilibrium position vector. Time is involved in that vector or no? Okay. Could you guess the next vector we have? Yeah, we call it x of t, and this would be x1 of t, x2 of t. How big is that vector? 2 by 1. Why is it 2 by 1? Because there's two masses. If it was a 3-mass 4-spring chain, how big would it be? If it was a 5-mass 6-spring chain, how big would it be? 5 by 1. There's a single entry for each individual mass, right? Okay. All right, so this is going to be the position of the center of mass vector at time t. What's the displacement? Yeah, so now you're into lesson 4. You just set up lesson 4. So this is going to be x1 of t, x2 of t, minus x1, x2. And what's that? x1 of t minus x1, x2 of t minus x2. And what are those? That's the first displacement function. That's the second displacement function. Does any of these have to do with the actual physical measurements? They can, but as we're going to see in this class, they don't have to. I can actually give you something within a millimeter using calculations, and then you can map that back to that thing, and you can confirm experimentally, which means I replace a physical problem with a mathematical problem. Depending on what I give you, if I give you the displacements and you calculate the masses that are required to generate that displacements, we're going to call that matrix vector multiplication. If I give you the masses, aka the forces, and you calculate the corresponding, then that we'll call that non-singular linear systems problem. If I say that t is going to be any time within a time frame, we will call that an eigenvalue problem rather than an algebra problem. Algebra is discrete. Eigenvalue represents something under that's continuous. Should we take a break?